Welcome to a lesson with Dr. Powell. Let's briefly talk about a couple different ways, which we will expand upon later, that a function can fail to be continuous at a point. Continuous at a point means that at that point, as we draw on either side, it's connected. And we'll actually make that definition rigorous later. So this function is continuous right here at this point. Namely, if we were to make a hole at this point, the y value that fills in the hole is already the y value of the function. That's another way of saying that the function is continuous. So a function is continuous right there. Now, what would make a function not continuous? Well, either there's a domain problem. In other words, the point is not in the domain of the function. Or there's a jump. Technically speaking, domain problems don't really count because they're not, technically speaking, in the domain of the function. So really, jumps are the only types of discontinuity that we mainly have. However, they come in various forms. And sometimes we don't call them jumps. For instance, what if something is oscillating so rapidly to a point and then rapidly away from the point, and it's oscillating so quickly, infinitely fast, that there's no way, maybe at this particular x value, of assigning a value that would actually make it continuous. That's one particular example of something of something like a jump that's not really like a jump. Kind of like a jump because it's way too jumpy. Maybe call that an oscillating discontinuity. So jump can take various forms. Jump can just look like this, as usual, but jumps can also take various forms, and we'll discuss this more another time too. What if we actually just keep going down an asymptote right here at this particular value? That would also be a jump. Domain issues. What if the function is just plain not defined at that point? Well, a function cannot be continuous at this point unless it's defined there. So this right here is called a removable discontinuity, because if you simply just redefine what the domain is of the function, it all of a sudden is continuous. But not all kinds of domain issues are removable. This one's not. You can't just assign a y value here. That doesn't work. There's no way of doing it because the limit does not exist. If the limit exists, then you can easily just assign the value of the limit to the function itself and make it continuous. Otherwise, there's no possible way. So this would be a domain issue. Other domain issues can be infinite jumps, like if there's an asymptote, or something of the form like this. In these particular cases, we just say the function's not, well, this point is just out of the domain. Function cannot be continuous outside of its domain because the function is not defined there. A function, we can only really discuss continuity of a function at points that are in its domain where it's actually defined. So perhaps we can say that this isn't really an option, it's just a domain issue. So a function is continuous on its domain precisely when you don't have jumps. At least this isn't really precise, but at least intuitively, when you don't have anything jumpy. Now, keeping that in mind, we actually can list out every single function that we normally consider that's nice is basically a continuous function, such as tangent, because it's continuous on its domain. I mean, there's asymptotes all throughout it. But all the issues that make it not continuous, these jumps, aren't really, technically speaking, jumps because they don't look like this. Rather, they look like this and this, where you might consider this as being infinity and negative infinity, if you will. But it's basically just an issue of not being in the domain. Tangent of x is a nice continuous function on its domain where it's defined. Similarly, cotangent sine x is continuous anyway, and its domain is everything. But even 1 over x is a continuous function on its domain. So we can kind of use these ideas when we're thinking about functions. Most all the functions that we work with commonly are continuous functions. Unless we kind of move along to piecewise functions, then we can come up with all kinds of examples of things that are not continuous. Such as, what if we had f of x is equal to x plus 1, where x is greater than 2, and when x is less than or equal to 2, then maybe it's something like negative x minus 5. Then, of course, if looking at this, let's take a look at the limit as x approaches 2 from the right side versus the left of f of x. So what does the graph of the function look like to the right of 2? The graph to the right of 2 is this one. And if it were connected all the way to 2, to x equals 2, then we would fill in this hole. Basically, it would be the value of this function definition at 2. We simply just plug 2 into this to see what the right-hand limit would be, and we'd end up getting 3. Now for this one, we just simply plug in 2 into the definition on the left side right over here, and we see that the limit is negative 7. Notice how this is not equal to this. Therefore, no way it can be, no way you can redefine this function to make it continuous. It is a jump, and 2 is in the domain. So we end up getting something along the lines of this. Let's see. So we end up getting, if I use my eraser here, a hole right here going up, and then somewhere down here eventually you have this, and it goes like that. So notice how we have this jump. So this would be a point of discontinuity of the function. Thanks for watching.